Hi, my name is Jenna Saylor, and welcome to my Physics Lab #1 presentation. Yay, physics, woo! So, the purpose of the lab was to observe the motion of a computer model object based off of physics principles, observe the motion of an object moving at a constant velocity without changing direction, compare the results and draw conclusions, discuss potential error, and answer what-if questions, and then have fun, of course. So, some important concepts to understand are Newton's second law of motion, force equals mass times acceleration, and this basically means that an object of a certain mass also needs a certain force to accelerate. So the stronger the force and the lower the mass, the more the object's going to accelerate. Another principle to understand is the momentum principle. Momentum equals mass times velocity, or force times change in time. So basically the applied force over time is momentum that carries an object forward. There's also 4 fundamental forces that are just good to know. The only one really taking place in this problem is gravitational, because it's keeping the pencil moving across the table. But there's also a strong and a weak force, which is usually between particles, and then electromagnetic. Another thing is net force. Whenever the net force is the total force like on a system in every direction. When there's 0 net force, that either means the object's at rest or it's moving at a constant speed. And then finally, there's instantaneous and average velocity. We don't really calculate it for this, but it's also just good to know because you can look at it by looking at the slope of the time versus position graph, but it's basically change in distance over change in time. And then instantaneous would be the tangent to the graph. So, the preview. The observed model had a smaller velocity in comparison to the predicted model, which we will get more into later. The system for the experiment was the desk, the pencil, and the force exerted by my hand, while the surroundings was everything else. And then the pencil is initially at rest with a speed, velocity, displacement, acceleration, and net force of 0. So we're gonna take a look at the computer model. First, discussing the code, there's a basic template for it, but I went ahead and changed a few things to make it more accurate towards my actual experiment. I changed the mass of the ball, which is also the pencil, to 0.0201 kilograms, which is just the weight of my pencil. I changed the initial velocity vector to 0.1, or not initial velocity vector, but the velocity vector to 0.154, which is the slope of my actual recorded experiment. So it's just the velocity of the pencil, so the online experiment could simulate it more accurately. And then delta, that was just like the frames, the same frames that were used in my recording. And then finally, the ball position, I just changed it to the same as it was in the real experiment. So, as you can see here, after the virtual one ran, there was the position versus time graph, and then the constant velocity, and we'll get more into that later. But now for the actual experiment, I recorded the motion of an object moving at a constant velocity in one direction. I uploaded the video to Tracker, and I analyzed the motion and viewed the information to graph. And then I used an online graphing program to plot both the predicted and observed results together to compare them. So right here was my actual observed results. You can see it looks pretty similar to the online model, and then here's just the video from the experiment. Okay, discussing the results in comparison to the computer model / whatever. So the observed results had a smaller average velocity in comparison to the predicted results. As you can see here, blue is predictive and red is the observed. This will also be talked about more in the next slide. If the orientation of the axes were to be switched around, so instead if it was the x positive direction, it was x negative, the magnitude of the velocity would stay the same, but it wouldn't be in the same direction because it's moving, or it wouldn't be like the slope wouldn't be the same because it would be going in the opposite direction. So instead of a positive magnitude, it would be negative. So like if the initial velocity was 10 meters per second, it would instead be negative 10. And the predicted model has an object with 0 net force, which explains why the object moves at a constant velocity. If there is a force acting upon the object, it would accelerate it and not move at a constant speed. 0 net force doesn't necessarily mean the object's at rest, but just moving at constant speed, just like we mentioned earlier. So it just means the forces are balanced. So there are a few potential errors in the experiment that made the observed a little different from the predicted results. Because our actual experiment wasn't in perfect conditions, there was never going to be no friction. The resistive forces acted on the system and made the object slow down or not necessarily travel at a constant speed. Also, the starting force wasn't like necessarily continuous, it was like a little unbalanced. So yeah, the unbalanced forces were one of the main causes for deviation between the two results. And if it was to take place in ideal settings, it probably would have been a lot more accurate towards the predicted model. So yeah, and then once again, the friction caused the object to slow down and not necessarily travel at the same velocity the whole time. In the future, a more precise and accurate constant force could be applied to the object and also a friction-free zone in order to get best results. And that is it.